Ladies and gentlemen, today we gather to reflect on a mind that reshaped our understanding of reality itself. A thinker who dared to ask the most dangerous questions the universe could offer, and who refused to be limited by circumstance, convention, or even the boundaries of the human body. This is the story of how modern physics was changed forever by one extraordinary intellect. For centuries, the universe was treated as a grand but predictable machine. Time ticked forward the same for everyone, space was a silent stage, and black holes were cosmic prisons from which nothing could ever escape. These ideas were comfortable, they were neat, but they were incomplete. Then came a radical shift, one that challenged what scientists thought they knew about time, space, and the very origin of everything. One of the most profound changes came from reimagining black holes. Once believed to be eternal voids that swallowed all information, they were transformed into dynamic, physical objects with temperature, entropy, and even a slow, ghostly glow. This single idea shattered a long-standing belief in physics and forced scientists to confront a terrifying possibility that the universe might not always preserve information. Whether the debate is fully settled or not, modern theoretical physics was permanently altered. From that moment on, black holes were no longer just endpoints of dying stars. They became laboratories for testing the deepest laws of nature. Equally revolutionary was the way the beginning of the universe was approached. Instead of treating the Big Bang as a mysterious singularity, where science breaks down, new mathematical frameworks were introduced to describe the birth of time itself. The idea that the universe could be finite yet without boundaries, much like the surface of the Earth, changed cosmology from philosophical speculation into a rigorous, testable science. Suddenly, the origin of everything was no longer beyond reach. It was something humanity could attempt to understand. But perhaps the greatest transformation was not just in equations or theories, but in how physics was communicated to the world. Complex ideas about relativity, quantum mechanics, and cosmology were translated into language that ordinary people could grasp. Millions who had never opened a physics textbook began to think about time slowing down, space bending, and the universe having a beginning. Modern physics stepped out of ivory towers and into living rooms, classrooms, and curious minds across the globe. This shift inspired a new generation of scientists. Young students who once believed physics was only for geniuses or prodigies saw proof that curiosity mattered more than perfection. That asking big questions was more important than having immediate answers. Research today in quantum gravity, string theory, and cosmology still builds upon those foundations. Entire fields exist because someone refused to accept that the universe was unknowable. And then there is the human example. In a world obsessed with speed, appearance, and convenience, here was proof that the power of the mind could transcend physical limitation. Productivity was redefined. Genius was redefined. Success was redefined. The message was clear. Intelligence is not measured by how fast you move, but by how deeply you think. Courage is not the absence of struggle, but the decision to continue despite it. Modern physics today is more daring, more philosophical, and more human because of this legacy. Scientists now openly discuss paradoxes, uncertainty, and the limits of knowledge. They accept that not all answers come easily, and that some of the most important discoveries begin with a simple sentence: what if we're wrong? So when we ask how modern physics was changed forever, the answer is not just found in textbooks or research papers. It is found in a mindset that encourages bold questions, embraces uncertainty, and believes that the universe, no matter how vast or strange, is something the human mind can strive to understand. Ladies and gentlemen, the universe did not become smaller because of this work. It became more meaningful. And in understanding it better, humanity learned something equally important, that even in the face of overwhelming odds, the pursuit of knowledge can be limitless. For a long time, black holes were seen as the darkest dead ends in the universe. According to classical physics, once something crossed the event horizon, it was gone forever. Its matter, energy, and information erased from reality. These objects were thought to be perfectly black, cold, and eternal, obeying gravity alone and nothing else. This view fit neatly within Einstein's theory of general relativity, but it created an uncomfortable wall between gravity and quantum mechanics, two pillars of modern physics that refused to agree with each other. The revolutionary shift came when black holes were no longer treated as silent cosmic prisons, but as physical systems with measurable properties. By applying quantum principles to the edge of a black hole, it became clear that empty space is not truly empty. Instead, it seethes with virtual particles constantly appearing and disappearing. Near the event horizon, this restless quantum activity produces a subtle leakage of energy, allowing black holes to emit radiation. This idea was shocking because it directly contradicted the belief that nothing could escape a black hole. This radiation meant something even more radical. Black holes have temperature and entropy. They obey the laws of thermodynamics, just like ordinary objects. Suddenly, black holes were no longer abstract mathematical curiosities. They became real physical entities that could slowly lose mass and eventually evaporate over unimaginable timescales. This forced physicists to rethink the nature of space, time, and energy at the most extreme limits of the universe. Even more unsettling was the implication for information. If black holes can evaporate completely, what happens to the information about everything that fell into them? Quantum mechanics insists that information cannot be destroyed, while gravity seemed to suggest that it could vanish forever. This conflict ignited one of the greatest debates in modern physics, drawing in generations of scientists and reshaping entire research fields. As a result, black holes became testing grounds for the deepest laws of nature. They are now central to research in quantum gravity, string theory, and holographic principles. What was once considered a theoretical curiosity turned into one of the most powerful tools for understanding the universe. By redefining black holes in this way, modern physics was forced to confront its own contradictions, and in doing so, it took a massive step toward a deeper and more unified understanding of reality itself. For decades, the origin of the universe was treated as a boundary where science simply stopped. The Big Bang was described as a singularity, a point of infinite density and temperature where the known laws of physics break down. At that moment, time itself was believed to begin, leaving scientists with equations that worked everywhere, except where they mattered most. This gap turned the beginning of the universe into a philosophical mystery rather than a scientific problem. A new way of thinking changed that perspective completely. Instead of accepting the singularity as an unavoidable failure of physics, advanced mathematical approaches were introduced to describe the early universe in a smoother, more coherent way. By blending ideas from quantum mechanics with gravity, it became possible to model a universe that did not start with a sharp edge in time. Rather than a violent point of creation, the beginning could be understood as a gradual transition, where time behaved more like space and the universe had no distinct boundary. This idea fundamentally altered cosmology. It suggested that the universe could be finite in size, yet endless in structure, similar to how the surface of the Earth has no edge despite being limited. The birth of the cosmos was no longer an unknowable moment hidden behind infinities. It became something that could be explored with equations, predictions, and observational evidence. By reframing the beginning of everything in this way, cosmology evolved from speculation into precision science. Questions about why the universe looks the way it does, why it expanded, and why physical laws appear finely tuned became legitimate scientific inquiries. This shift opened new paths for research in inflation, quantum cosmology, and the nature of time itself, permanently changing how humanity studies the origin of the universe. For much of scientific history, physics was built on principles that were treated as absolute. Among the most sacred of these was the idea that the laws of nature are perfectly consistent, and that certain quantities, especially information, can never be destroyed. This belief sits at the heart of quantum mechanics, ensuring that the universe is predictable at its deepest level, even if it appears chaotic on the surface. Gravity, however, told a very different story, and the clash between these viewpoints exposed cracks in what scientists once believed were unshakable foundations. When extreme cosmic objects were examined more closely, it became impossible to ignore those cracks. If matter carrying information falls into a black hole, and that black hole eventually evaporates, classical reasoning suggests the information is lost forever. This conclusion was deeply unsettling, because it implied that the universe might not obey its own most fundamental rules. Instead of quietly accepting this contradiction, long-held assumptions were placed under intense scrutiny, forcing physicists to question whether their most trusted laws were truly universal. This challenge did not merely create confusion, it ignited progress. Entire generations of physicists began re-examining the meaning of information, causality, and determinism. The debate pushed science beyond comfortable territory and into a realm where paradoxes were no longer signs of failure, but clues pointing toward deeper truths. Concepts such as holography, entropy bounds, and quantum entanglement gained new significance as possible ways to resolve the tension between gravity and quantum theory. What made this shift so powerful was its willingness to embrace uncertainty. Instead of protecting existing theories at all costs, modern physics adopted a mindset that allowed even its most cherished principles to be questioned. This intellectual courage changed how research is conducted. Today, physicists openly discuss the limits of knowledge, acknowledge incomplete theories, and explore ideas that once seemed too radical to consider. By challenging assumptions that had stood for decades, the field of physics became more flexible, more honest, and more innovative. The result was not the destruction of scientific law, but its evolution. Modern physics now accepts that true understanding may require rewriting the rules themselves, and that progress often begins when the universe forces us to admit that what we once believed to be permanent may only be part of a much larger and more profound reality. One of the greatest unsolved problems in science has always been the conflict between relativity and quantum mechanics. Relativity explains gravity and the large-scale structure of the universe with remarkable precision, while quantum theory governs the behavior of particles at the smallest scales. Both are incredibly successful, yet they speak fundamentally different languages. For decades, physicists treated this divide as an unfortunate reality, believing that a complete unification might be impossible. That belief began to change when bold attempts were made to explore where these two theories overlap. By examining extreme environments, such as the edges of black holes and the earliest moments of the universe, it became clear that neither theory could stand alone. Gravity could not ignore quantum effects, and quantum mechanics could not escape gravity's influence. These boundary conditions turned into testing grounds where new ideas could emerge. This shift pushed modern physics toward the concept of quantum gravity, a framework that seeks to describe gravity using quantum principles. While a final theory remains elusive, the direction of research was permanently altered. Ideas such as extra dimensions, vibrating strings, and the holographic nature of space gained serious scientific attention because they offered possible bridges between the two frameworks. Perhaps most important, this effort changed how physicists think about unification itself. Instead of forcing one theory to dominate the other, the goal became understanding how both might arise from a deeper underlying structure. Modern theoretical physics now revolves around this pursuit, with countless experiments, simulations, and mathematical models inspired by it. The search for a unified description of nature is no longer a distant dream. It is the central driving force behind much of today's most ambitious scientific work. Complex physics was once locked behind equations, universities, and academic journals, accessible only to those with years of formal training. Concepts like black holes, time dilation, and the origin of the universe felt distant and intimidating to the general public. This separation created the illusion that modern physics was too abstract to matter in everyday life, and that only a select few could ever truly understand it. That barrier was broken when these ideas were explained through clear language, vivid metaphors, and powerful storytelling. Instead of overwhelming people with mathematics, the focus shifted to the meaning behind the ideas. what it actually means for time to slow down, for space to bend, or for the universe to have a beginning. Suddenly, millions of people around the world were thinking about cosmology, asking questions about existence, and feeling connected to the vastness of the cosmos. This accessibility transformed public science culture. CS became a source of inspiration rather than intimidation. Students who had never considered a career in science began to imagine themselves exploring the universe. Teachers gained new ways to spark curiosity in classrooms. Society as a whole developed a deeper respect for scientific thinking, critical reasoning, and curiosity. By bringing modern physics to the public, science stopped being distant and became a shared human journey of discovery. For generations, scientific success was often associated with physical presence, speed, and traditional measures of productivity. The image of a scientist was someone standing at a blackboard, speaking clearly, moving freely, and working within rigid institutional expectations. This narrow definition quietly excluded many brilliant minds and reinforced the idea that limitations of the body also limited the power of thought. That perception was fundamentally changed by a life that demonstrated the opposite. Intellectual achievement was shown to be independent of physical strength, appearance, or conventional ability. What mattered was clarity of thought, persistence, and the courage to keep questioning when circumstances made everything harder. This example reshaped how the scientific community and the public view capability itself. Research culture began to evolve. Greater emphasis was placed on ideas rather than physical presence, on depth rather than speed. Collaboration, patience, and long-term thinking gained respect. Young scientists learned that setbacks, whether physical, personal, or professional, are not disqualifications, but part of the journey. This shift encouraged inclusivity and diversity in science, allowing more people to see themselves as contributors to knowledge beyond laboratories and universities. This message reached society at large. It challenged the belief that value is tied to perfection or convenience. It showed that resilience is not about overcoming difficulty once, but about continuing every day despite it. By redefining what it means to succeed, modern science adopted a more human, compassionate, and courageous identity, one that recognizes that the greatest breakthroughs often come from minds that refuse to be limited by circumstances.